So I think it's time to start. Good morning, everybody. Welcome to the first colloquium of the Faculty of Physics in this spring semester. Before I introduce Andrzej, let me just tell that the next colloquium is in 4 weeks. I think it's the 3rd of April, just before the Easter break. So Andrzej is, so to say, an internal guest here. He works on, he's an expert on special relativity and quantum theory of information. And today he will give a talk devoted to his work somehow on the crossroads of these two fields. Please, Andrzej.
Thank you very much. I hope I can be heard. Nope. I can relocate the microphone perhaps. Is it better? Even up. Okay. I will try to be loud then. So let me begin by going back to one of my favorite tales in contemporary physics. This is a picture taken from the textbook on quantum theory from lectures on physics by Feynman, where he discusses the double slit experiment. He discusses the unusual properties of quantum theory, and he claims that, in fact, you can understand most of the quantum theory based on this experiment, and all the crucial elements are already here. And he lists those elementary properties of quantum theory that are crucial to understand the whole theory. And first of all, he points out that reality is not fully predictable. One cannot predict results of single quantum mechanical experiments. Therefore, nature is fundamentally indeterministic. And second of all, another unusual, unclassical property of quantum theory that objects behave as if they were moving along several paths at the same time in this particular experiment, in which an electron behaves as if it was going throughout two paths at the same time. And on top of that, there is a certain rule of how to compute probabilistic outcomes of these experiments. And all these three elementary properties, in a way, come out of the blue. They are postulated in quantum theory. Nobody knows where they come from. And Feynman concludes, let me read the whole quote. One might still ask, how does it work? What is the machinery behind the law? No one has found any machinery behind the law. No one can explain any more than you have just explained. No one will give you any deeper representation of the situation. We have no ideas about a more basic mechanism from which these results can be deduced. And the purpose of this seminar is to discuss these two papers, where we propose a very unorthodox approach to this problem. And if one adopts this approach, then it is possible to gain some new insights into the questions asked by Feynman. The first paper was written with Professor Dragan from University of Oxford. He is most known for the discovery of quantum cryptography. The second paper was written in a larger collaboration. It was a recent one, published just several weeks ago, with Kacper Dębski, my PhD student, Szymon Harzyński from this faculty, as well as Krzysztof Turzyński. And we kind of generalized these ideas that were presented in the first paper. And let me first summarize the claims that we make, and then I'll try to advocate for them. So first of all, we work in special relativity, and we claim that special relativity can be extended to describe frames of reference and particles moving with superluminal speeds. And such an extension does not lead to logical or causal paradoxes, but instead it leads to certain disturbance of causality in a way that is known from quantum theory. So when you try to extend special relativity in this way, certain problems with causality appear, but these are not really logical inconsistencies, but rather something that looks like what we know from the quantum theory. And namely, in such an extension, the fundamental indeterminism or unpredictability of particle decays becomes a necessity, as well as the fact that particle can not only move along single trajectories, but it is not possible to avoid situations where motion takes place along multiple trajectories at once, which is kind of a version of the superposition discussed in the double slit experiment. And finally, when one looks at possible relativistically invariant descriptions of a probabilistic theories characterizing such motions, then these theories must involve something that looks like complex probability amplitudes, to put it short. So obviously, this is a controversial topic, and I will try to kind of address all possible objections one by one. So first of all, it is kind of unusual to talk about superluminal particles or objects in relativity simply because it looks like Lorentz transformation fails or breaks down for velocities larger than c. If you just look at Lorentz transformations, you immediately see that they do not make any sense for velocities that are larger than c, simply because what you get is irrational numbers, imaginary numbers that don't have any physical interpretation. So it simply looks like it breaks down. However, this is not exactly the case, because when one derives these transformations, there are certain assumptions that one takes. For example, one assumes that principle of relativity applies, so the transformation must be linear, and they also should preserve the speed of light. And it turns out that this is not the only solution that you get out of these postulates. There is another one that is less known. And while the first one is only valid for velocities that are smaller than c, there is a second family of solutions that only makes sense for velocities that are larger than c. And you can directly substitute these transformations to see what happens to a ray of light. For example, a space-time interval in this simplified 1 + 1 dimensional case has this property that it's still 0 when you make a transformation, which means that both of these transformations preserve the speed of light. Which means that when you want to derive special relativity, you have these two possible mathematical solutions. They both satisfy all of your requirements, and now it is a matter of your choice whether you want to keep them both or you reject one of them as unphysical. But in that case, you will have to take another postulate to remove that possible mathematical solution as unphysical. So, and what the purpose of the talk is to investigate what happens if you do not take that extra postulate, if you keep both of those possible mathematical solutions on equal footing. Okay, so geometrically speaking, the first transformation is a hyperbolic rotation, which means that if you move, that essentially means that your axis of a moving observer that corresponds to his time is tilted. The same is for the spatial axis, and the angle of that rotation of the axis has to be smaller than 45 degrees, so that these axes do not cross the light cone here. The second family of solutions is also hyperbolic rotation, but for angles that are larger than 45 degrees, and they correspond to a situation where time axis is on this side, spatial axis is on this side. And in particular, you have this extreme case of situation where an infinitely fast moving observer would have a transformation that simply changes time and space, exchanges the roles. And obviously, this is physically hard to interpret. This is the purpose of our work, to try to interpret this. However, mathematically, at this stage, there is nothing wrong with these transformations. Another objection is to say that it takes an infinite energy to exceed the speed of light. Is this true? Yes, it is true. One cannot accelerate anything above the speed of light because that takes infinite energy. However, for the very same reason, when one derives expressions for relativistic energy and momentum of a particle, the same derivation leads to another solution that is usually excluded, that has the following form, where energy and momentum of a particle is only well-defined for velocities that are larger than c. And similarly, these properties for energy momentum are such that when you try to slow down an object characterized by these expressions, it takes infinite energy to slow it down below the speed of light, which means that it is true that you cannot cross the speed of light, but in principle, you have ready-to-use expressions to characterize possible objects if they existed. That would characterize their energy and momentum. Sometimes it is claimed that superluminal particles, or tachyons, are, as they called, corresponds to imaginary masses, which is not true. the reason for this claim is that if you take a square root of -1 here, which is an imaginary unit, you can absorb it into mass, and that means like mass is imaginary. This is not entirely true because there is this extra factor sigma here that appears, that can take a value of plus or -1, and that factor has a non-trivial transformation properties that we have derived in the papers, and that means that it's not as simple as just taking mass to be imaginary. There is some more non-trivial transformations there. However, what I'm saying is that mathematically speaking, there is nothing, these are valid solutions. Now, but this is not the most important objection against such extensions. The crucial objections deals with causality, and the argument against superluminal objects in relativity goes as follows. Consider two resting observers, Alice and Bob, that want to exchange a superluminal particle or signal, or suppose it's a signal. And the signal starts at A, it moves superluminally, it's absorbed at B. Now, it is easy to show that there always exists another inertial frame of reference in which the order of these events is completely reversed. In that other frame of reference, absorption at Bob takes place before the signal was sent in A. Which means that if in one frame of reference Alice wants to send something to Bob, then in another frame of reference it is Bob that sends the signal to Alice, which is a bit absurd because it looks like Alice can affect the past, which is against our experience, against all laws of physics. One cannot affect the past simply because that could lead to possible causal paradoxes. For example, I could shoot my grandfather, and therefore the whole story wouldn't make any sense. And this is the really important reason why not to take these extra mathematical solutions seriously. However, what we have pointed out that this argument is fundamentally flawed, and it is missing one important point. So let me go back to the reasoning and discuss what happens when Alice wants to send a signal. If I want to send a signal, for example, I have a gun, I want to shoot a bullet that moves superluminally, I must have two things. First of all, I must have bullets that move superluminally. They must exist as physical objects. And second of all, I must be able to control my gun, to pull the trigger or not pull the trigger at will, so that I can send information, because information must be under control. I cannot send something randomly. I must control my source of information. So that means that in the past word line of Alice, there must be some mechanism, some physical process that she can control, and she can pull the trigger if she wants to send a bullet or not send a bullet. In quantum theory, these kinds of ideas are usually called hidden variable theories, where they when one assumes that there is certain reason within a particle to behave in a certain way. A classical idea of a system that has certain gears and wheels inside that determine the exact moment at which the process will happen. So suppose that Alice has a gun like this, there is a process like this, and she sends the bullet at certain moment to Bob. Now, according to Bob, he is being hit by the bullet at this point, but before that happens, he is completely unaware of that. He cannot predict that in advance, which means that he is a completely independent observer far away. He has no idea that he is about to be shot, which means that in his past, there is no information about the event B. So by just observing himself and his past, he will not be able to predict that a bullet is about to hit him, which is kind of trivial. But let us now go to the second frame of reference and ask the following question. In this other frame of reference, it looks like it is Bob that is emitting the particle. So what was the absorption becomes the emission. And let us ask the question, what caused that emission? What is the reason why this particle was emitted at B? So let us notice that in the first frame of reference, there was no cause for the absorption. So in the second frame of reference, locally here, there can be no cause for the emission, because that process cannot simply appear because we have changed the frame of reference. which means that what one could say that the reason for that emission is a bit absurd because it takes place far away here at Alice's gun. And such a theory is possible. Such a non-local theory of this is possible, where the cause of that emission is far away and possibly in the future, but such a theory would not be local. And if you are looking for a local and deterministic theory that predicts that emission in this frame of reference, such a theory cannot exist. Therefore, for an observer that is sitting next to Bob and only can observe what happens next to Bob locally, this process will appear to be completely spontaneous and completely unpredictable, or as we like to say in quantum community, indeterministic. Therefore, so this is already interesting because we have started with special relativity, and we have a completely reasonable theory apart from having these crazy objects, but you can see that this element of local unpredictability appears very quickly as a must. You cannot simply avoid this. Not only that, I told you about Alice and Bob, but if these Alice and Bob guys were actually particles, identical objects, then there is no reason to make this frame of reference preferred from this one, because it is simply the same story in different frames of reference. And if you want to impose principle of relativity that says that all frames are equal, then we should not make this frame preferred from this one. And the only way to make this whole thing consistent is to say that if the first frame has no deterministic and local description of this process, then the first frame of reference can also have no local and deterministic description. Which means that the only way out is either to say that these superluminal particles are unphysical and rule them out, which is always an option, or not to do that, but then one is forced into saying that if those particles existed, they would have to be emitted completely spontaneously, or, as I said, indeterministically, so that there is no classical local deterministic theory to predict when that is going to happen. So if I had a gun, I would never know when this gun is about to shoot. That's the putting it short. And for that reason, it is quite interesting that if you had a gun like this, you could not communicate with that gun. You could not send any signals with it, because to send signals, you must control your gun. If you cannot control your gun, you cannot send signals. So there is not really a paradox, because you would have a paradox if you could signal superluminally. And it turns out that if you even try to do that, you cannot. It is not straightforward how to signal, even if you had a gun that shoots superluminal bullets. So this is one of the observations that if you dare to examine what happens if you do not rule out these extra solutions from special relativity, unpredictability or indeterminism becomes necessary. So one could summarize this, that if there was no deterministic, this is essentially saying the same thing. By the way, let me point out that this year's Nobel Prize in Experimental Physics was for the experiments that proved that no local and deterministic description is possible in quantum theory. And it's quite interesting that it is possible to explain violations of Bell's inequalities experiments with a non-local deterministic theory or local indeterministic theory. So there are two postulates, locality and determinism. You can rule out one of them, but the other can be kept. So you could have a deterministic theory that is non-local, exactly like in this scheme here. So I discussed what happens in the case of these unusual superluminal particles, but what happens to the case of normal particles, like ones that we know of and that we can examine in experiments. So consider a decay of a normal particle, like subluminal particle, into a pair of particles, and the question is whether this can be completely deterministic or not in this framework. So the underlying assumption of what we're doing is that all frames are equal, and we are treating both families of solutions on equal footing, including the superluminal frames of reference, which means that I should be able to describe this process in the superluminal frame of reference. And the question is, how does it look? So if I go to a frame of reference that moves infinitely fast, which is the kind of simplified version, that simply corresponds to changing time and space in this simplified 1+1 dimensional scheme at least. And that process corresponds to a diagram like this. So for the superluminal observer, All these particles are already superluminal, and they decay like this. So what appears to us to be normal particles, to a superluminal observer, appears to be a tachyon. However, for tachyons, I have already argued that decays involving tachyons must be fundamentally indeterministic. There is no local and deterministic way of describing superluminal particles and their emission. And for that reason, if from the point of view of the superluminal observer, this process involves tachyons, therefore cannot be deterministic, then if we impose principle of relativity that says that processes or events take place independently of who observes them, then the same lack of deterministic description must characterize the observer that is subluminal. So that argument kind of shows that if we allow superluminal observers to describe what we observe, then because of that, simply because of that, these decays would not have any local and deterministic theory behind them. So this is essentially simple argument. It's almost trivial argument, but it shows that what was fundamentally unknown in quantum theory that has to be assumed as a great mystery. Why is it that a particle pops out of nowhere for no reason from an atom? Why this atom emits something spontaneously? It is a mystery, but if you take this approach, this becomes almost trivial. I mean, there is no other way. It must be that elementary processes are completely unpredictable. What about the second part, and what about superpositions? And another, yes? Yes. No, I just said that you cannot send signals with a speed greater than light. No, I'm saying that it is not possible. Wait, I mean, you are asking different questions. I said that even if you had superluminal particles, I don't know how, at least, that I can say, I don't know how to send superluminal signals with these particles, because you cannot control the source. In order to send signals, you must control the source. Otherwise, it's not a signal. It's just a randomly emitted bunch of objects. Yes. And it's not, yes. So you're asking how, so you're asking how is it? Yes, in the orthodox quantum theory, there is no superluminal signaling. Yes, so you're asking how is it possible that we don't observe that complete randomness for normal particles? Is this the question?
Pniewski.
Your argument goes this way. We cannot have deterministic theory, so we have to go to quantum theory. And then this lets us have this superluminal signals.
I'm not saying you have to go to quantum theory. I'm saying that if you allow superluminal particles, indeterminism is inevitable, that you cannot have a fully classical theory. I don't know if the quantum theory is the only one that is the theory we need, but you cannot have a classical theory. That's what claim number one. And claim number two, the usual argument against these extensions of special relativity fails, because in principle there is a way out. You can have a non-deterministic theory.
The process you describe is also a quantum process. In the sense it's undeterministic, but it doesn't mean that you can send infinitely fast signals.
Yes.
Anyway, you break causality in this way in quantum theory too. So this is not argument. You're just saying, I don't know. Okay, I agree. You don't know.
Let's postpone this to the question section.
I'm not sure. Okay, I'm not sure if I understood the subtlety of this question. So let me also point out what else is inevitable when you seriously take these extensions of relativity. So consider a process in which a particle, for example, a photon, moves from A to B, but in between it's reflected from a mirror. So there is a photon that goes from A to M, then it's reflected here and goes to B. Now, if I want to detect that photon, I could place a detector on the way. Oops. Sorry. I don't know. I did something illegal here. We need to go to full screen again. So if I want to place a detector here, that detector can click and detect my photon and absorb it. But then if I place another detector here between mirror and B, that second detector will not click. I can have my photon only in one place, not two. So thank you. So if my detector detects a photon here and makes a click, then if I place another detector over here, that second detector will not click, and vice versa. If the second detector clicks, then I have certainty that no other detector could absorb my photon before. Now let me write down the exact same process from the point of view of the observer that moves superluminally, for example, the one that moves infinitely fast, in which case I'm flipping time and space. And that same process looks like this, where now you have to completely reinterpret what's going on. What you can see here is that there is certain point, a mirror, that seems to emit a pair of photons, one going to the left, one going to the right. And so it seems that the photons are multiplied. However, when you take two detectors and place them to detect your photon, place them here and here, then from the previous story, you already know that only one of the detectors will be able to click. You'll never hear two clicks in your experiment. You can have only one. But if you take away the detectors, the motion of a photon seems to be characterized by two paths that are simultaneous. So you have two independent paths that take place at the same time, which, I mean, it's hard to resist the comparison with the double slit experiment, where you have exactly the same thing. If you do not observe your photon, it seems to move along multiple paths. But if you do make an observation, you can only find your photon at one place, never two places at the same time.
A detector between M and B. Then in first picture, we have a photon coming from A to the mirror, and then from mirror to the detector, right? If we have a detector between M and B, only one.
Yes.
But in the other picture, we would have one photon going from M to detector, located between M and B, and the other photon going from M to A. And so there would be a detector that absorbs a photon, but there would be also another photon going from M to A. I don't see how that obeys what we know from physics.
Well, okay, so one thing. Okay, this is true. What you have pointed out is a really nice observation, because indeed, if you place a detector over here, then it seems that it can make a click, and yet you have this line, yes?
Yes.
Well, that is certainly true, but only when you have a theory that preserves certain direction of time. For example, I have said that my photon was emitted here and went here and ended up here. That theory, that narrative simply prefers the one direction of time. Now, I'm not the one, I don't understand how it happens that photons appear to move along one direction of time, not the other, but in principle, equations are time invariant. So I would say that if you have a preferred time in one of the frames, that would be a problem. If you do not have a preferred direction of time in any of your frames, then you cannot make that argument. So that's my only comment on this. But just to make very precise statements I want to make, if you do not make any observations, if you have no detections along the way, it looks like you have two trajectories attached to a single photon. But if you make an observation, if you place two detectors, you will never find the photon at two places. This is all I'm saying is this. Yes, yes. And that could be a problem if the theory preferred one direction of time. If you do not make that distinction, then you cannot make that argument. Yes, invariant of the arrow of time is the same up and down. Now, this concept can be easily generalized in the following way. So if you already believe, if you already know that you can have situations where your particle moves along two paths at the same time, so to speak, then you could consider a situation where a particle moves like this, is scattered somehow, and then goes into this weird state of moving along two paths at the same time. And then if you take this process and observe it from a superluminal frame of reference, or make this superluminal transformation, now you have three trajectories attached to a particle, and you can easily iterate it to eventually end up with a situation where you can't really avoid schemes where you have particles moving along multiple paths, in this sense that you, if you don't make any measurements, you will have to have a kind of kinematics that characterizes motion along from A to B along multiple paths. Now, there are certain insights you can have from this. For example, you could ask, what happens if you try to consider a process like this, where you have multiple paths connecting two points, and you want to somehow characterize this dynamics in a certain way, moreover, if you try to assume that your description must be relativistically invariant, so that in all frames of reference, description must be the same, then you simply have to use some sort of relativistic invariance to characterize motion like this. For example, if you have a single path in space-time in an orthodox scheme, the simplest relativistic invariant is the proper time along the path, or expression like this. I denote it with a phi because this proper time, this integral, which is relativistic invariant, has this nice property that you can write it in the following way, where it looks like an integral of E times dt minus P times dx, where E and T are expressions for energy and momentum of your particle. And it's the same expression. Up to a multiplicative constant is the same expression. This is the simplest relativistic invariant that characterizes a single path in space-time. This is, by the way, a question that Feynman asked: how is it possible that non-relativistic quantum mechanics has E times dt minus P times dx all over the place, although this is a non-relativistic theory? He pointed this out in several of his writings. So now we are facing the question how to characterize a diagram like this. Is there a relativistically invariant description of this? And if we want this to be invariant, a natural assumption is to say that we want to look for mathematical objects that are functions of proper times along all the paths. So if you have n paths, you would like to look for quantities that are functions of proper times along each of the paths. And since there is no preferred labeling of these paths, your functions, whatever they are, should be completely symmetric. So if you take a function of all the phases and you introduce some permutation of the indices, the function should be the same, simply because there is no preferred path one from the others. Also, if you want the theory to be time invariant, time reverse invariant, then flipping the direction of time corresponds to changing phase into this phi into minus phi, which means that your theory should have, your quantity should satisfy the following property, where if you flip all the signs, you get the same thing. And now, I haven't specified what that function p even is. I am saying that this would be a relativistic invariant that does not prefer direction of time or choice of the labeling. However, since I know that no deterministic motion is possible here, no deterministic theory is possible here, I would like to look for a theory that is probabilistic in some sense. Suppose that I want to find possible probabilistic theories characterizing motions like this. And what does it mean for the theory to be probabilistic? Well, if you want to find some sort of probability that characterizes this image that is relativistic invariant, then that quantity should satisfy some properties of probability. Unfortunately, in quantum theory, probability has different properties than in classical theory. For example, it is not additive. In a double-slit experiment in classical theory, you'd simply add probabilities, but you cannot do that in quantum theory because you have to add amplitudes. So there is something wrong. And the question is, what do you really even mean by saying it's a probability? Fortunately, there is one property of probability that is completely universal and does not depend on whether theory is classical or quantum. That property is multiplicativity of probability. If you have two independent processes that follow each other, then probability of the whole is going to be product of probability for the first one and for the second one. And for that reason, if you consider a special case of motion where the diagram you want to have is looks like this, where all the paths cross at a single point, and you want to characterize this diagram, then you would say that probability of the whole, this function p for the whole, should be a product for this part on the lower part and the upper part. And that mathematically means the following equality. Since phase is additive because it's just an integral, this means that your function p should satisfy this third axiom, so to say, of probability. Now this is all, and it turns out that the number of solutions of these simple assumptions is very, very limited, which is a surprise. There is very few mathematically allowed functions that satisfy these axioms. The third one looks a bit like an Euler formula for exponential function, by the way. And this is a generalization of Euler's functional equation. And it turns out that the simplest possible solution of this has this form, where the function p is a constant times sum over all the paths with the exponential functions with some exponential factors alpha, I don't know what it is, to an arbitrary power gamma times the same thing with the minus signs to the same power gamma. And this is the simplest solution. There are some more complicated solutions as well, but the simplest one is this one. Now, this already looks a little bit familiar, but there is one problem. Alpha can be any number. We don't know what alpha and gamma are. But if you want your theory to be right to characterize motions where not finite but infinite number of paths is considered, that would correspond to a situation where you have to sum infinite number that are greater than 1, infinite number of numbers that are greater than 1, and that would not be finite. If you want this whole sum to be finite, if you want to be sure that you have a chance to have it finite, the way out is to say that alpha must be purely imaginary number. Because in that case, you can sum up infinitely many phase factors, but they sum up to something finite. And that's why if you want the p to be invariant and finite, then the only way out, I mean, the simplest way out would be to say that you must attach a phase factor or phase complex number to each of the paths, sum over all of them, and take a modulus, in fact, to an arbitrary power. But then perhaps you can you can use some normalization arguments to say that the powers cannot be really arbitrary. It's the same because yes, for negative gammas it would be also fine. Yeah. So no, negative gammas. Well, then you'd have a 0 then. If gamma was negative, then you are at risk that your p is always 0, which is also not a very useful invariant. It is always 0. So we haven't pushed that really very far, but one observation is that if you want to look for any type of probabilistic theory that is relativistically invariant, you have very limited number of solutions. And this already looks like the simplest one looks very familiar. So there are some bits and pieces that start kind of start to look familiar. Now, the serious objection that people raised is, does it all break down in 1+3 space-time? Because what I have said so far is a simplified version when I only considered one dimension of time, one dimension of space. Does it make any sense to talk about this in 1+3 dimensional space-time? And essentially, the problem is the following one. If you look at space-time interval in 3 dimensions and consider 4-dimensional space-time with observer moving along the x-axis with a velocity that is superluminal, then that transformation corresponds to flipping x and t, and that results in the following transformation properties for this space-time interval, where you flip x and t, and you have to introduce 2 more variables characterizing your space-time coordinates in the superluminal frame of reference. Let me call them psi prime and chi prime. Now, the problem here is that all of these three variables, t prime, psi prime, and chi prime, are characterized by the same sign. They have negative sign, which is hard to interpret because normally you have a time that has an opposite sign to all the space coordinates in your space-time interval. Here there is more than one. The natural thing to say is that you need to collect those three numbers together and introduce a vector t and write your space-time interval in this way. Unfortunately, this is very, very strange because one doesn't know what it means. You have multiple, it looks like you have multiple time dimensions and single spatial dimensions in the case when you are moving superluminally. And that looks already, if what I said before is not enough, then this is even more strange. But however, it turns out that if you just close your eyes, go forward, and see what happens, like what are the consequences of this, it looks much more reasonable than it looks. So first of all, if you try to imagine that we need to construct kinematics in space-time that has more than one temporal dimensions, we are facing serious problems to talk about even about the simplest things, like what is velocity. Velocity is the derivative of position over time, but now if you want to compute the derivative of single position over free time, how do we proceed? So the paper that we wrote recently that was published in Classical and Quantum Gravity solves this problem, and we can essentially develop the whole kinematics and dynamics of that theory that has this hypothetical property that you have multiple times in the superluminal frame of reference. And in particular, we derive explicit formulas for Lorentz transformation that is generalized to any number of dimensions, 3 dimensions of space. And also, we derive the definition of velocity. That is the only one that makes any sense. I mean, you just derive it from using elementary properties of kinematics. This is the definition of velocity you need to use in that unusual case where you need to compute the derivative of single spatial position of the modulus of t times such a nice versor. And what comes out that if you take that definition of velocity, you can derive the following velocity transformation formula. And one interesting property of that formula is that with that definition of velocity, the speed of light is still preserved, which means that if the subluminal observer observes something that moves with the speed v equals to c, then for any superluminal transformation, this factor is finite, this factor is finite. What is on the left-hand side has also to be 0. Has also to be 0 because the right-hand side is 0, the left-hand side must also be 0. That means that the velocity from the point of view of the superluminal observer must also be c. Which means that with that unusual definition of velocity, the speed of light is preserved even for the 4-dimensional transformations. Again, which means that if you ask your students to derive all linear transformations that preserve the speed of light, then Lorentz transformation is not the only answer. There are also possible answers that have these unusual physical properties. The question is how to interpret those properties. This is an open problem. What I'm saying is that it is not as completely idiotic as it looks at first. And if there are reasons to reject these solutions as unphysical, I'm not saying it is not, these reasons do not exist. I'm simply not aware of these reasons. Maybe there are, but it's not as simple as saying that you end up with it is not as simple as saying that you end up with some grandfather paradoxes or transformations do not exist. This is not true. Maybe there are some deep reasons why this is not physical, this is just mathematics, but at this stage, without referring to arguments in quantum field theory at least, I'm not aware of these reasons. And the final questions, is this just math, or there is a chance to have any objects that correspond to that branch of mathematics, so to say. So this is something that we have tried to understand for a couple of months and we failed. Also, there were papers about quantum field formulations of tachyonic fields in the past with some of really good physicists involving Sudarshan, Aharonov, Saskind, Feinberg, who introduced the term tachyon. And to our understanding at this moment, all these approaches are completely wrong. I mean, there are certain flaws of this approach. So there is no good quantum field theoretic description of tachyons. Is this a problem? Well, in a way it is. Because if you look at quantum field theory of spontaneous symmetry breaking processes that usually involve diagrams like this, then the Higgs mechanism in particular, that is characterized by a diagram like this, where you first start with a theory that has a potential like this, and that potential is completely symmetric. However, spontaneous fluctuations result in some the dynamics of the system that drives the system to the local minimum, and the local minimum of the potential looks already like this and looks familiar. Then you can quantize the theory over here, and you end up with a well-known quantum field theory of Higgs particles, where other particles acquire masses because of that process, and that violates the symmetry because of the quantum fluctuations on top of the potential. What is usually not discussed or overlooked is that in order to have a theory like this with this potential, you must have something that is called a tachyonic field, which has a square mass term that has the wrong sign. For a regular quantum field theory of scalar particles, your potentials is parabolic. Here on top, the potential is inverse parabolic, and for that, the mass of your field must look like as it was imaginary. That's why the usual argument. So here you have explicit a physical scenario where, in order to describe Higgs mechanisms, you must start with tachyonic fields. One usually says that this is not physical. What really becomes relevant is already after the violation of symmetry here, where the particles acquire mass. However, the fundamental field that you start with has this potential. And what is interesting that nobody even quantized that field at the very beginning. Usually people quantize the field already here. There is no quantum field theory of this whole process. And that's what we have tried to find for the past couple of months, and we failed. But what I'm saying is that in order to have full quantum mechanical characterization of this process, you should be looking for quantum mechanical description, and you should try to answer what does it mean for your field to have a negative square mass. Yeah. Yes. I'm almost done. So then you can tell me apart in 5 seconds.
Let's wait for 2 more minutes.
Yes, I'm almost finished. So essentially, I'm saying that there is a slight hope that there may be something in that we observe already that may need an extra description that we are missing. And maybe the questions whether it really is completely meaningless to talk about superluminal particles or not is not as close as it may appear to be. And with that, I'd like to thank you. These are the papers.
Thank you.
Yeah, can you go back to this picture of the potential? So this is a legitimate potential, and this at the top we have tachyon, what means that the state of the system is in unstable state, and then it decays, and there is no superluminal signals at all in this process, and it's well known, and it's also described. So this is, I don't know why you're saying that this is, somehow you join the tachyon with the superluminal particles, but this is not the case here. There is no superluminal transferring of signals of any physical quantity.
May I answer?
So this is not the case.
So this argument that you're making is by Acharonov, Saskind, and Komar. They wrote a paper saying that if you had a field of a negative square mass, then in that field, under certain assumptions, there is no superluminal propagation, although your field is formally tachyonic because it has the inverse square mass. Now, the problem with that is that if you try to construct explicitly the theory talking about, quantum field theory, that describes these fields in second quantized picture, these theories do not exist because they make no sense. Saskind has tried, Feinberg has tried, and this theory that assume orthodox commutation relations between field operators fail. They don't make any sense. So I would say that if the argument you are making, that Saskind and Acharonov made, that there is no superluminal propagation, would make sense if the theory behind it made sense, but that theory doesn't make sense. What I'm saying that you need to probably modify the commutation relations in your field operator, And if you do, then it's not straightforward anymore whether the propagation is or is not superluminal for that theory.
Okay, so maybe if you want to have superluminar propagation, you need something like a stable ground state. Otherwise, you cannot say anything about propagation, because if the theory is unstable, it means everything decays, and there is nothing like stable excitation about that stuff. So, and we know quantum theory, full quantum theory of this stuff. You can quantize it in any minima, and then you have in the full picture, even with this picture which you have, even with this decay. So that's, you don't have to, you cannot quantize around maximum because you have this instability, but it doesn't mean that there are superluminar particles, as you're saying.
Well, I don't know that. You may be right that, that the only property that appears if you consider negative square mass is just instabilities of fields. That is the common belief. Unfortunately, there is no consistent theory of that. That's what I'm trying to say. And let me also point out that the orthodox formulation assumes that fields commute outside of the light cone. The field operators commute. This is the postulate that you put with your hands, because you take the Lagrangian of your theory, then you add commutation relations that come out of the blue, and then you end up with a theory that looks that it only is unstable but doesn't lead to superluminal propagation. However, your assumption that you make your operators commute outside of the light cone already puts with hands that you exclude solutions that propagate infinitely fast, and therefore they also cannot propagate at any superluminal speed. So in a way, you assume this. It is not a consequence. It's your assumption that does not lead to a self-consistent theory, by the way.
Okay, so I don't agree.
Okay.
Means that there is causality.
Duly noted.
So this is a causality. If you want to discard causality, you cannot discard this commutation.
I'll be more than happy to continue the discussion. We are very interested in this.
Okay, can I have a question as an experimentalist? Do you think these superluminal particles could contribute to dark matter and dark energy in the universe?
I don't dare to make any speculations like this. I have no idea. All I'm saying is that I'm aware that it's considered to be obvious that this makes any sense. This doesn't make any sense, that it's completely idiotic to even talk about this. This is a common conception. What I'm saying is that it's not too obvious to me, at least. If there are reasons why it's not possible, I don't know anything about that, certainly. My only hope for a possible experimental claims of any kind for this is that if we could somehow quantize our theory without making the approximation that we are only sitting here, but if you want to have a full quantum theory that allows for large energies, sufficiently large energies that will probe the existence of this local maximum here, which probably is beyond any experimental reach at the moment, then such a theory could perhaps point out that Higgs particles for sufficiently large energies could behave as fields that propagate in a way that either is unstable or superluminal. I don't know this because we haven't formulated the theory, but somehow we should be able to probe this for large energies. And that will be a departure from an orthodox theory where you have a quadratic potential. And that's what people call tectonic fields.
So again, well, it's far beyond my ability to comprehend the theoretical side, but for me the main question would be, could you imagine this, how to formulate, for example, gravitational interactions for these superluminal particles?
I mean, if principle of equivalence holds, then all objects must fall at the same rate, and that includes superluminal particles. If principle of equivalence holds, which means if gravity is equivalent to acceleration, then if I have a bunch of particles moving horizontally, so photons, tachyons, normal particles, and I accelerate up, then all of these particles will fall down. So if principle of equivalence holds, then these particles should gravitate the same way that everything else. So for that reason, I would rather say that this is not a good candidate for dark matter if these particles existed, or dark energy, because dark energy is supposed to have the opposite impact than regular matter. So my not very educated guess says it's not going to help.
Okay, so my intuition would say that if particles travel with speeds larger than speed of light, they would tend to somehow inflate the universe, but okay.
If principle of equivalence holds, that means that these tachyonic particles should gravitate the same way as everything else.
We have a question here, please.
Oh, sorry. So just
Could you show us the slide number 1?
Of course. I assume it's not my name that you're interested in. This one?
No. The one, the first slide.
Well, this is the first one. Ah, sorry.
No.
This one?
No, the first one.
Ah,
The first.
sorry.
The first one. This one.
Ah, Feynman. Okay, sorry.
I would like to make some comment on this. What we see here? We see here 3 material objects: electronic gun, diaphragm, and a screen. As we know, material objects are made of matter, and matter interacts with space, making it deformated. So all these material objects deformates the space they are in. So at which position electron knows everything about this space configuration? At the moment of leaving the electron gun.
Sorry, you've lost me at the first sentence already. I'm not sure what you mean by the objects deform space. We are talking about special relativity, where space
So
is fixed
matter interacts with space, making it deformated. So also, because all these objects are material, diaphragm, screen,
Okay,
and
this is true in general relativity, but I'm not going into general relativity. This is special relativity, where you assume that these deformations are negligible. I'm not taking them into account at all.
But I would like to know at what position electron knows everything about space and material objects they are in this space. At the moment of leaving electron gun. And what's more, the
I don't think
precedent.
that electron knows anything. It's just a simple object. We here work at the approximation where there is no deformation of space due to matter.
But the space is deformated because they are material objects. They are small, but nevertheless, they deformate space.
Yeah, this is a topic for another seminar. I'm not discussing this.
Yeah, I'd like to note that at the moment when the electron leaves the electron gun, the screen and this barrier don't have to exist yet.
I mean,
Right.
in a way, my one comment I would like to make is that I would be very happy to find out that there is a simple reason we have missed, that this makes no sense whatsoever. And I kind of challenge everyone to propose that.
so
Yeah.
can we go back to the potential for a
Yes,
moment?
yes. The last slide then.
Yes. Right.
Not at this.
Yeah, but I just wanted to comment that I don't quite see what this has to do with superluminal propagation, because it seems to me that what you're trying to do is to expand around the minimum, which is fine. But again, well, coming back to the previous comment, it's not impossible to have a solution where the field is on the top, but then you cannot just assume that the field is constant everywhere. You need to have some sort of stable solution, which with this potential cannot be done, I think. But there can be ones where you have a local minimum and the field is there.
Yes.
But then you have to take into account that your ground state is not just the constant field everywhere plus oscillations, but it's some non-trivial configurations. And you can, I believe, produce quantum corrections to that. It's not a problem, conceptually.
You can? You say you can? Yeah, I didn't hear you. Did you say can or cannot? So there are several theories. For example, George Sudarshan, who is famously unrecipient of Nobel Prize 7 times, so he has not received it, but he claimed he needed one. He claims that you can have a theory that is completely reasonable, and he constructs a theory that unfortunately violates very elementary principle that creation operator does not have an eigenstate. So he was making like simple errors, and I'm not aware of a fully quantized picture of this potential. I mean, we are trying, myself and Krzysztof Torzyński and Szymon Harzyński and other people, we are trying to find one, and we have failed so far miserably for some time. And if you are aware of a scheme that is fully quantized, I'll be really happy to investigate it. But I'm afraid it's not there. So the usual picture is you have classical theory, you hand wave that there is some quantum fluctuations that will be unstable, and then you quantize when you're already fine in the minimum. I'm not aware of anything else. Yes, that is true. So yes, of course, you expect that the quantum field theory will have instabilities, and it's very, very probable that there will be no stable ground state for that theory. I mean, this is one of the possible pictures that we are aware of this, obviously, right?
No, that's the difference. I think that there is a stable ground state. It's in the minimum. So it's just that assuming that the field is at the maximum everywhere and trying to expand around that.
That is true, but you see, this is already a self-interacting theory. This is a theory where you have a self-potential phi to the 4, right? If you take a free field, and you want to start with a free field, that is a common approach in quantum field theory, you have a theory that is only characterized by potential that is inverse parabola, and that theory has no stable ground state. And if you want to start with a free theory, you already failed there. And we don't know what it means. Maybe it means that the theory doesn't exist. Maybe this whole thing breaks down in quantum field theory, who knows? Or there is something that you need to change in the fundamental ideas about how do you approach this problem. Maybe the orthodox quantization is not right for these types of fields. Maybe we need to change it, and then who knows? What I'm saying is that I would rather first have a quantized theory, then say what are their properties, instead of saying that theory must certainly be this or that, although this theory does not really exist. So to me, it's an open question.
Okay, being an experimentalist, I would expect to see one of these particles in my lab. But anyway, I have many questions, but the first one is that I didn't really get that, why you are trying to connect your studies with basic quantum mechanics, because what you have done so far is another approach or the solutions for the STRs. And what we call a particle is the unitary irreducible representation of the Poincare group. So you are dealing with only the Lorentz group basically here. The other question is that when you are dealing with these trajectories of the particles, for example, from A to alpha and alpha to B, those are like the way you described it, like mutually exclusive to each other. So I don't see that those are being some of our all trajectories and all histories and all that. And what you are getting is the solution as a number. So why you are trying to connect all these things with quantum mechanics? In the first place, I don't understand this.
Okay. So my understanding is this: in quantum theory, you first postulate that physics is not completely unpredictable, that you have fundamental indeterminism that is there, and you only have to deal with probabilities.
That quantum physics came much later than the STR. It's 1905. So you have a solution at 1905. Think that you are sitting in 1906. You have another approach to the STR, and this is what you are dealing with.
Yes.
Then why you are bringing the quantum mechanics here?
Even better, because you can derive special relativity not even knowing that speed of light is constant. You can derive special relativity based on Galilean's principle of relativity.
We forget about the photons. You are talking about only photons.
I
would take a fermion, which is having more, the intrinsic spin.
So you are asking, how do I connect this to quantum theory, yes?
Where? I don't see in your slide where you are trying to quantize with your new approach something. Like say, the formal approach is that I would start with a Lagrangian. Action, and then what I will do, I'll do some gauge transformation, do some renormalization and all that, and at the end of the day, I'll use some cutoff and then get some interaction, which can I see in the lab. This is what I will do, and then I know that this is the merge of the STR and the quantum mechanics. More specifically, it is the merge of the Minkowski space and the Hilbert space. This is what we do. Now here you are dealing with, I don't know whether these, like when you alter the sign of your the time coordinate, I don't know whether those are going to satisfy the Euclidean analytic continuation when we deal with the weak rotation and all that in quantum.
You ask way too many questions.
Yeah, I have a lot of questions, to be honest.
I don't understand.
Most important thing is that I don't see the link between quantum mechanics and what you do.
Okay, so first of all, in order to even start any quantum mechanics, to have any algebra, any mathematical postulates, such that you have Hilbert space, that you have, I don't know, tensor product structure, that you have to second quantize picture, all these things are secondary. You first have to know that even there is a need for quantum theory, you have to know that physics, there is no classical physics description that is possible. And how do you know that? You don't. You know that from experiments. For example, this year's experiments have shown that there is no local and deterministic description of reality. And it doesn't matter whether quantum theory is right or not, there is no going back to classical theory. We don't know that because you have to postulate it in quantum theory. And then when you know that, you construct probabilistic theory of some sort. But so this approach is to kind of justify why why reality is not classical, why you must have indeterministic element in your reality, where you must have, when you must face with situations where particles are not moving along single trajectories, but along multiple trajectories, and eventually why you must use some sort of complex numbers to characterize these motions. Now behind this, there is this whole machinery of quantum field theory where you have extra mathematical formulation of this, but you even have to start with the motivation, why reality is not deterministic and predictable. And although this seemed to be a mystery, and Feynman understood this as the most difficult question that drives everything else, we try to propose an approach where these features of reality are trivial consequences of principle of relativity. So this is a starting point for the quantum theory. I'm not saying this is quantum theory. This is a starting point, a motivation for quantum theory that was missing so far because you had to postulate these things out of the blue.
Okay, I think it's time to finish at this moment, really. Thank you, Andrzej, again.